In today's video, we're going to discuss the conservation of energy. We're going to have a conversation about conservation, if you will. So we're first going to talk about mechanical energy. I'm hiding the answer here so you don't see it. And then we're going to derive the equation for the conservation of energy. And we're going to simplify it to the point where you go from this complex equation all the way to the simple equation that only contains a few variables. Then we're going to solve this problem, which is an MCAT style problem. And finally, we're going to go over this diagram to really drill the concept of the conservation of energy home. All right, let's get started. So before we talk about what exactly the conservation of energy means, let's discuss what mechanical energy is. So for the purposes of the MCAT and your introductory to physics class, the mechanical energy is composed of two forms of energy, kinetic energy and potential energy. When you add these up, they will equal the mechanical energy. Let's break this down a bit. So here I've written out the equations for kinetic energy and potential energy. I derive these equations in an intuitive to understand way in the other videos, so you can refer back to those. You'll find them in the description box down below. But the idea behind the conservation of energy is that in a closed system, the mechanical energy of that system will be conserved, meaning the initial mechanical energy will always equal the final mechanical energy, like such. Since the initial mechanical energy equals the final mechanical energy, then it necessarily follows that the initial kinetic energy plus the initial potential energy will equal the final kinetic energy plus the final potential energy. Now let's just break this down further. All right, so this is a huge equation, but we can simplify it so that we don't have to deal with a bunch of numbers on test day. Notice that mass is on both sides of the equation in every single term. And of course, the mass is going to be the same because it's of one specific object. So we can just cross it out of the entire equation like such. All right, so this looks a bit more manageable, less variables to deal with. But what if I told you we can simplify it even further to reduce the likelihood of any error occurring on test day? So I'm going to explain what's going on in this problem right here before we simplify it further. So the idea here is that we have a ramp at a 2-meter vertical height at a 45-degree incline from the ground, and you have this steel ball that's 70 kilograms that's rolling down the ramp. Now, importantly, pay close attention to the wording of the question. So when they tell you that a ramp is at a 2-meter vertical height, that means that they're talking about from the top of the ramp all the way down to the ground, so like the shortest path to the ground. They're not talking about the length of the ramp. And as we'll see, we don't even need to know the length of the ramp to figure out what the velocity will be right before the ball stops. All right, so now let's apply this scenario to our equation right here. Well, we can simplify this even further because notice how at the beginning, right before the steel ball starts to roll down, it's at rest, meaning its velocity is equal to 0. And then notice how right here, right before it stops, its height is also at 0. So its final height is 0. So this means that this term and this term are going to be equal to 0. So we can simplify the equation to GH initial equals half V squared. It literally feels like magic. You go from this complex, long equation to just having this very short equation. Let's plug and chug now. So as you can see, I went with 10 for gravity. On the MCAT, you can always round it up to 10. Times 2, that's 20. And then on this side, we have half V squared. We don't know what V is. That's what we're trying to figure out. So now let's just multiply both sides by 2 and then take the square roots to find our answer. All right, so 40 isn't a perfect square, so we don't really know what the square root of 40 is, but we know what the nearest two perfect squares are. So if you go below this, then you have 36, the square root of that is 6. And if you go to the nearest square root or perfect square that's above this, then you have 49, which the square root of that is equal to 7. So it's somewhere between 6 and 7. But of course, 40 is a lot closer to 36 than it is to 49. So I would say it's closer to 6. So I'll go with like 6.2, 6.3. Either way, you don't have to be exact on test day. The answer choices will always allow for an approximation because obviously we don't get a calculator on the MCAT. All right, before I leave you, I wanted to explain the conservation of energy in one different way very quickly to really drill the point home. All right, so here we're essentially holding a ball at a distance away from the ground and we're just about to drop it. Right before you drop the ball, as you can see, mechanical energy is at 100%. And all of that mechanical energy is in the form of potential energy because the ball has not started to move, so it has no velocity, so there's no kinetic energy. As you drop the ball, once it reaches like halfway, now half of the potential energy has been converted to kinetic energy. Notice the mechanical energy has not changed because mechanical energy is conserved. So initial equals final. Now, once the ball continues to fall, right before it hits the ground, you maximize the kinetic energy, but because you're almost at 0 meters away from the ground, there's no potential energy. So the idea is the amount you decrease potential energy by, you increase kinetic energy by that same exact amount, and then mechanical energy is always gonna be conserved. If you found this video helpful, like and subscribe to stay up to date with all my content, and share this video with your friends. It really helps the channel grow, and I would really, really appreciate it.